Happy to see still some faces, and I think you are also enthusiastic, so I hope it's not going to be boring too. I'm going to talk about part of my PhD research, the programmable pointing effect, and also suppressing torsional buckling in metamaterials. These are connected, but actually they are separate parts of my PhD thesis, which I handed in last month, so basically I almost finished my PhD. I haven't defended yet though. I work in Wageningen University, and I noticed that most of you don't know where is it. Wageningen University is in the center of, almost central part of the Netherlands, and that's the image of the campus, and they work a lot on environmental related things and like major issues and stuff. So about the pointing effect, first let's go with an introduction. What is the pointing effect? Poynting designed an experiment. He pulled a piano wire and designed this torsion experiment. He applied twist to the wire, and he observed that the wire elongates when it is under torsion. And then he studied it a bit further with, analytically, and observed that this pointing this elongation is the result of this normal force response, which actually occurs in nonlinear materials. And it is quadratically proportional to the shear strain, with a coefficient that we call it Gn, or pointing modulus here, after pointing. And of course also we have in this linear shear stiffness or shear stress response as well, which is linear, and the coefficient here is Gs, shear modulus. So we have shear modulus, Gs, and the pointing modulus. Comparing these two, for a material like rubber, the pointing modulus is conventionally positive, and also it's almost half of the shear modulus, but not always. There are some, for example, biopolymer networks that they show negative pointing modulus. So it means that when you shear them, they want to contract. And it's a bit weird, but they know why now. Anyhow, that actually triggered us to ask the question whether we can program the, if I find the pointing response. So let's a little bit, I want to explain it a bit more. What happens if the pointing modulus is positive? This is what happens. You can twist the material under two boundary conditions. If it is fixed load boundary condition, then the positive pointing modulus would lead the extension of the cylinder, as you can see in the left, or dilation. But if it is under a fixed gap boundary condition, when you twist it, a positive normal force would emerge that you can measure, for example, with a rheometer. But if we have a negative pointing modulus material, this is going to be reversed. So under fixed load, we are going to have a contraction, and under a fixed gap, we are going to have negative normal force. And we ask whether we can program this with metamaterials. And of course, people do all sorts of weird things with metamaterials, and so why not? The answer is yes, but how? We designed this cylindrical structure, the thing that you see in the right, and we also model this with this spring model network, which are just Hookean springs, and this is just an elongated beam of this network. As you can see, it's pretty simple. I mean, it's not as complex as we really simplified it to understand what's going on there. And what we have is one spring that actually can bend at the nodes, and it can also experience contraction or extension, of course. But when it bends enough, one thing that can happen is that let me take this and say for example, here this can touch this when they bend enough, meaning that the vertical beam can go through contact with the horizontal beam. And this contact, we also consider it in our model. And we're going to see that how it changes the response. So first, let's talk about the compression. We just compress the system. What we observe is this torsion. But again, we can compress it under different boundary conditions. We can compress it while it is clamped, like in the right. But we can also compress it while it is free at the top, so it rotates. So basically the location of this rotation, the maximum rotation changes in these two conditions. But what we have in the force response or compression stress is 3 different regimes of deformations. Pre-buckling and then the buckling regime. And then here what we see is the self-contact regime that the structure stiffens again. And then let's see what happens to the structure under torsion. Initially, when we twist the structure, a negative normal force occurs, which basically represents this negative Poynting modulus of us here. But if we pre-compress the structure a little bit, then we see that we are in the buckling regime and the normal force actually is almost 0. But if we pre-compress it a bit further, then we are in a regime that we call the self-contact regime, where the normal force and the Poynting modulus becomes positive. And if you compress it further, still positive, but smaller. As you can see, the curvature here is smaller. So this shows that the Poynting modulus actually is what we call programmable. And let's look at it in a more detail in this graph. The Poynting modulus, real-scale Poynting modulus, as a function of the compression strain, changes like this. Initially, it is negative. Then in the buckling regime, it becomes 0. Then it shoots up to a high positive value, and it declines by increasing the pre-compression. And what you see on the actually at the inset is the just the results of the model, which is basically which coincides nicely with the experiment. And here we have shear modulus. That also shows interesting behavior. Initially, it is a small positive value, but in the buckling regime, the structure softens and it is almost 0. Again, in the self-contact regime, shoots up. And also interesting, but this is what one other thing that you can notice here is that the order of magnitude of Gn is like, it is 1 order of magnitude than Gs in some specific compressions, which is very unconventional. And another thing is that what happens to the material under large torsional deformations, what we see when it is pre-compressed to the contact regime. As you can see, the normal force and the Poynting modulus both oscillate. And also the shear modulus and the shear response. That also oscillates, but I don't show that here. And to understand this behavior, we need to study the system to what happens to the system in this structural limit and what happens basically in the continuum limit as well. So, and we did that. I shortly introduced what we observe, but I'm not going to dive into this. This is kind of a line of a different project that I wouldn't discuss much about it. But just the result is that in a continuum limit, we observe that actually there is a topological kink in the system. And then we can move this kink by shearing the structure, which makes it interesting because basically we can program it where we want to put it in the structure. Again, a different line of the research. I'm not going to dive into it, just quick result. The second part, I think you can interrupt me if you have any question, but yeah, feel free. The second part of this talk is going to focus on twisting materials, but different type of materials. Still twist. And what happens if you twist a Coca-Cola can is what you see in the left picture, or I can just show you here. Just crumpling, yeah? And that's the result of all the bucklings and fractures, if there is. Just these complex mechanics that happens in the system. But if we want to prevent this, we can make it a bit thicker. But that wouldn't prevent it, actually. If we make it thicker, we can still make it buckle and flatten if we twist the system. But we actually found out that if we use auxeticity, we can make a cylinder that doesn't basically buckle under torsion, and it's really resistant under extremely large torsions. And let's first see how we design it. It's pretty simple. This is pretty famous auxetic system, which is designed in metamaterials. We have, this is just basically what they call supercell. So you repeat this and you have your 2D system. And here we have, this is the small thing here, the contour is a unit cell, which is oriented in this, in the vertical direction. But if we can change this orientation by just rotating the system, rotating the grid, and design basically materials. And if we shear in this direction, for example, this one is asymmetric with respect to the direction of the shear. But this one is symmetric, this one also is symmetric. But let's see how this asymmetry combined with auxeticity affects the result. So we twist, symmetric, symmetric, and this asymmetric. So this buckled already. We twist further, and you see here this is contracting also, but buckles in the end. But what about this? This actually radially shrinks, and just this the shrinked area increases, and the whole system it's kind of a smaller cylinder, but it doesn't buckle until finally it breaks at the edge. And let's see what's happening to this cylinder in more details. First of all, here I plot the radial strain as a function of the shear strain, and also the axial strain as a function of shear strain. The radial strain linearly increases for, I'm discussing two asymmetrically designed cylinders with different angles. We see that radial strain linearly increases by increasing the shear strain or torsion. And at some point, of course, it saturates, like in this case, it does saturate. P divided by 6, that's the angle of this orientation, principal axis, and that's what we design now. What about the axial strain? Also, axial strain is quite weird because it is non-monotonic, which means that the pointing response is complex here. And this is kind of comparable with some fibrous materials, and also it is observed in pantographic materials, I believe. And also in this asymmetric system, we see that. So the torque response and the shear modulus also depends, of course, on the on this orientation of the unit cell. First, this shear modulus is for small deformations. It is smaller when the orientation of unit cell is horizontal, but when we twist it to the diagonal direction, the P divided by 4, then it becomes like the stiffest, we have the stiffest cylinder, which is kind of understandable. It's not really weird, I think, I would say. But what is weird is basically this buckling torsion and buckling torque for these different cylinders with different orientations. We observe that this buckling torsion basically, first of all, changes depending on this orientation. But secondly, in this asymmetric one, as I showed earlier, we don't see buckling. Basically, in the end, we see the breakage of these hinges. And the torque as well, depending on the direction, orientation of the unit cells, the torque also behaves differently. And interesting part is here that the system doesn't buckle, and if we go further, if we even break the hinges, or if we have stronger hinges, it just goes up, which we don't have it here, but I mean that's the limit that we could go with this system. And to understand this again, we look at the structural reconfiguration of the system. We have asymmetric one at the top and the symmetric one here. What happens with the asymmetric one is quite different than what happens here. So what we have initially is softening. When we shear the material, the hinges bend, and then there is a softening of the system. But then there is one thing that I should mention is that the shear strain can be actually splitted into compression and extension. We know that. So let's look at this system from that perspective. So we have shears that are combination of compression and stretching. So if this system is softening and there is compression and stretching in perpendicular directions, and if we see further, there is an alignment of the unit cells. They sit on each other, so they support each other. And also there is an alignment of hinges here. And if we continue with the torsion, this just doesn't change. And they basically, the reconfiguration plays in favor of resistance of the material. And even though in metamaterials we normally use these local bucklings to basically obtain different functionalities, but here we use local bucklings to prevent a global buckling of the system. And that's the irony here. And but in this system, which is symmetric with respect to the shear, that doesn't happen similarly. The reconfiguration is not really doing anything helpful, and it doesn't really stop the buckling. As you can see, there is no proper alignment. So in a bigger picture, I show the asymmetric one here, and these lines are showing this alignment of the unit cells, and which help with basically stiffening in the end. And here is this local stiffness of the material, of the system. And here the purple one is this asymmetric one, which initially softens and then stiffens and goes up. But in the other system, we have stiffening and then buckling. So that's the difference. I have also a little bit of information of what happens to the asymmetric shells. Of course, when you are compressing it, as I said, this one has a negative Poisson's ratio. So there is a little bit of contraction or radial strain, negative radial strain. But in this case, there is a positive strain, which means that this is a there is a positive Poisson's ratio here. And of course, you see that nothing is different but the angle of the orientation of the unit cell. So we clearly know these systems are anisotropic, but the point is that we can design this anisotropy to do something useful to the system, as we saw previously. And of course, we can also program the Poynting modulus in these symmetric systems, which I just showed that Gn also changes by precompression strain, but not as flexible as the previous system, and not large range as it. And also the shear modulus, it changes a bit, as you can see, for two different systems. Both of them are symmetric here, but still, yeah, it's not. The changes are not that large, but yeah, I mean, in this case it's a bit, but nothing very special. And to conclude, so we had two different systems, network of non-uniform beams and the asymmetric auxetic design, and we observed that here we can program the Poynting response and get oscillatory responses, and here also we can program the responses, we can get axial negative strain, and also we can suppress the torsional buckling in the end. So in the end, I would like to thank my advisors, my PhD advisors, Dr. Habibi, Professor Linden, and Professor Bohn, and also our collaborators, Dr. Kohle at University of Amsterdam, and also my master's student who contributed to the second part of this project, this talk here. So, Tobias, and finally, thank you for your attention.